So here is another problem. Feel free to pause the video to try and solve before we look at the solutions together. Now the question says that the frequency of a sonometer wire depends on the length, tension, and mass per length. So let's represent that with an equation. Frequency depends on the length, tension, and linear density. The extent to which it depends on these parameters was not given, so we represent that with an unknown. So frequency depends on tension to an exponent of x, tension to an exponent of y, and linear density to an exponent of z. We are to use dimension analysis, so let's look for dimension of each of the parameters. Dimension for frequency is going to equal t to the power of -1, because frequency is number of oscillations per time. It's measured in per seconds. Its frequency or its dimension is t to the power of -1. Dimension for length is L. Dimension for tension, since tension is same thing as Newton, tension is a force, it's measured in Newton, so its dimension is going to equal to ml t to the power of -2. That is mass times acceleration. The dimension for linear density is mass per length, mass per unit length. So its dimension is going to equal ml to the power of -1. So we have found the dimension of all the parameters. Let's go ahead and put an equal to the variation proportion that we have. So putting equal to the variation expression, we are going to have f equal to k, l to the power of x, t to the power of y, and coefficient of linear density, to the power of z. Okay. Now let's put in the dimensions of each of the parameters in the equation. Dimension for frequency is t to the power of -1. So t to the power of -1 equal, constant does not have dimension, leave it that way. Dimension for length is still L, so we have L to the power of x. Dimension for tension is ml t to the power of -2 or to the power of y. Then dimension for linear density is ml to the power of -1 or to the power of z. Going forward, we have t to the power of -1 equal to k, l to the power of x. We multiply all the exponents by y. So the exponent of mass here is 1. So m to the power of 1 is m to the power of y. L to the power of 1 times y is L to the power of y. Then t, -2 times y is -2y. Multiply by, this is m to the power of 1 right here. So m to the power of z is m to the power of z. And L to the power of -1 times z is L to the power of -z. Next thing we do is combine similar terms. So we have k, let's begin with m. M to the power of y plus z is going to give us m to the power of y plus z. Followed by L, we have L to the power of x here, L to the power of y, and L to the power of -z. So that is going to give us L to the power of x plus y minus z. Then lastly, we have only one t, which is t to the power of -2y. So times t to the power of -2y. All right. Now the next thing we do is to compare the left-hand side and the right-hand side. On the left, we have only t as the only parameters. On the right-hand side, we have m, l, and t as our parameter. So we see that on the left-hand side, two parameters are missing. We do not have m, we do not have l. Whenever a parameter is missing, what you do is you give the exponent, or you take an exponent of 0 for that parameter. That is, we say m to the power of 0, L to the power of 0, right? And we'll put that on the side in which is missing. So we'll put M to the power of 0 here and L to the power of 0. So we have not changed this equation at all because M to the power of 0 is 1, L to the power of 0 is 1. So it's like we are multiplying left-hand side by 1. So we have not changed it at all. We only did that so that we can have equal parameters on both sides. Now the next thing for us to do is to compare the left-hand side and the right-hand side. So starting with M, so comparing for M to the power of 0 is going to equal M to the power of Y plus Z. So this cancels this. 0 equal Y plus Z. Then we can say that Y equal to negative Z. Okay. So let's call this our first equation. Let's make this equation 1 because we cannot solve further from here. Now going forward, let's pick the next parameter. Comparing for L. On the left hand side, we have L to the power of 0 equal, on the right hand side, we have L to the power of X plus Y minus Z. So L cancel L, 0 equal X plus Y minus Z. We can make Z subject of formula. So we say Z equal X plus Y. So we cannot solve further. We'll call this equation 2. The third one, comparing for T. So comparing for T, the left hand side we have T to the power of negative 1. I mean from here. So T to the power of negative 1 equal T to the power of negative 2y. So T cancel T. We have negative 1 equal negative 2y. Negative cancel negative. We have y equal 1 over 2. So we've gotten y. Let me write it here. Y equal 1 over 2. So y is equal to negative 2. Quickly, we can find z then. Because from equation 1, we have y equal negative z. So we can say that z is equal to negative y, which means that z is going to equal negative 1 over 2 because y is 1 over 2. So z is equal to negative 1 over 2. Z equals negative half. That means we are left with only x. So now let's find x. From equation 2, we have that z equal x plus y. This is equation 2. So let's make x subject of formula. That means x is going to equal z minus y. Now, what is z? Z is negative half, negative 1 over 2. What is y? Y is 1 over 2. So we have negative 1 over 2 minus 1 over 2. Negative half minus half is going to give us negative 1, which means that x is equal to negative 1. So x equal negative 1. From our starting equation, we have f equal to k, L to the power of x, t to the power of y, linear density to the power of z. Now let's substitute the value that we have in the equation. So k equal L to the power of negative 1, t to the power of y is half, then linear density is negative half, which means that f equal to k, L to the power of 1, negative 1 is 1 over L, t to the power of half is same thing as square root of t, then linear density to the power of negative half is same thing as 1 over square root of linear density, which we can combine as k multiplied by 1 over L into, since tension and linear density both have square root, so we can put them together, say tension over linear density. So our final equation is going to equal K over L multiplied by square root of tension over linear density. So the equation connecting all these parameters from our dimension analysis is equal to K over L tension, square root of tension over linear density.